Hello, guys. Once again, I want to welcome you to our class. And in today's class, we are going to be looking at a very important topic, very, very important topic. As far as this Earth is concerned, as far as this cosmos is concerned, this topic is very crucial, very, very important. And that is what is called ecology. Ecology. So, what is ecology? The word ecology was coined from two Greek words, the oikos and logos. Oikos and logos. And oikos talks about the dwelling place of an organism. The logos talks about the study of it, the study of that dwelling place of an organism. So when we combine these two, we can answer that ecology is a study of the dwelling place of an organism. But to expand that definition, to make it complete, because it cannot study the environment of an organism or the dwelling place of an organism without the organism itself or without interaction between between organisms or among organisms, as the case may be. So you can't do that. You can't study the environment of an organism in isolation with the organism itself. So the organism has to be involved in this definition. And that is why, holistically speaking, we can now define ecology as the study of the interrelationship that exists between organisms and their dwelling place. And when I say their dwelling place, I also mean their environment. So you go to a place and you're studying uh, the organisms, different kinds of organisms in their dwelling place, that is called ecology. As simple as that. Ecology, the study of the interrelationship that exists between organisms and their external environment. And of course, you know that organisms do not exist in isolation with other organisms. They cooperate together, they work together, they interact together. And this interaction is also studied in ecology, the kind of interaction that exists between organisms of the same species and the kind of interaction that exists between organisms of different species. So all these things are studied within ecology. So the person who coined this name is a man called the Hacker many years ago, was the one who first coined the name ecology and termed it the study of the dwelling place of an organism. The study of ecology is so vast. And when I say so vast, a minute, and when I say so vast, I mean it's so vast. It's not something you can exhaust in one class. So we may likely have part one and part two of the study of this ecology. Because as you've always known, I wouldn't want the video to be too long. So I will take the first part of this ecology now, and in part two, I'll take the second part. So I'll be going through some basic concepts in ecology, and I'll be taking them one after the other, one after the other, one after the other. So, like I said, ecology is a study of the the environment, the interaction that exists between organisms in the environment. And when we say environment, we are talking about the physical and chemical factors within the surroundings of an organism. These physical factors, of course, it could be light, it could be temperature, and wind, topography. The chemical factors could be pH, could be salinity, and so on and so forth. So these are the physical and the chemical factors within the surroundings of an organism, and all these things are studied within the concept of ecology. Having given this background or foundation, we are now going to go into the levels of ecology. The levels of ecology. Now, in the levels of ecology, we have three different concepts to look at. I'll say rewrite this again. The levels of ecology, we have three different concepts. One, we have a minute. All right. So, when it comes to ecology, the study of ecology can be done at three different levels. We'll have the individual level, we'll have the population level, and we'll have the community level. This individual level is the lowest level in ecological studies. It's called the individual or species. That is one single organism. And this single organism could be a plant, could be an animal, or could be a microorganism. Now, when you leave this first level, or like I said, it's also called the species level, you now get into the second level that is called the population level. And at population level, you are now looking at the collection of individuals of the same species, no longer a single entity, no longer a uniform entity, but now you're looking at the collection of the collection of individuals of the same species interacting together in a given environment. And then it is important you note or you take note that one of the characteristics of population is the fact that they sustain the ability to interbreed together. So all the organisms of the same species in bacteria, for instance, interbreed together. Or for instance, Homo sapiens, all Homo sapiens, that is all humans on Earth, regardless the color or the race, are of the same species. And because they're the same species, they can interbreed together. So the collection of individuals of the same species and can interbreed together is what we refer to as what? Population. And in a typical population, we have what we call characteristics of a population. We have characteristics of a population. One of them is density. And when we say density, we're talking about the population size per unit area. That is one characteristic of a population. There should be that population must have a population size uh, per given area. That is the collection of individuals within that population. The density of the population is one of the characteristics. Population size, population size per unit area. Population size is a simple term, the total number of individuals within that population, or also referred to as its density. Then, of course, we have the death rate, the the rate at which individuals, you know, uh, live or get eliminated, or probably uh, a loss of individuals within the population can be referred to as the death rate. And of course, when we talk about the birth rate now, we're talking about addition of individuals within the population. So these are some of the characteristics. We have others like age distribution. Age distribution talks about the proportion of individuals of different ages within the population, the proportion of individuals of different ages within the population. Then we have dispersion. The way individuals are distributed within the population is what we call dispersion. The way individuals are distributed within the population is called dispersion. Then we have immigration. Immigration is, of course, the way talks about the addition of individuals within the population. Immigrants, that is people who come into the population. So the influx of individuals within the population, or the addition of individuals within the population, is what we call immigration. Emigration, of course, is the opposite of immigration. So all these are characteristics. So I want to list them now. Let me list some of these characteristics of a population. I don't want to clean this. I'll use it to explain when we get to food chain and food web. So, characteristics of a population. Number one, death rate. This is death rate. Number two, birth rate. Number three, dispersion. That is the distribution of individuals within the population. Immigration. Immigration. Growth rate. Density. I forgot density. Density. So these are some of the characteristics of a population. A given population must have these characteristics. The loss of individuals within the population, the rate at which individuals die within the population, of course, is the death rate. Then, of course, the rate at which individuals are added to the population is the birth rate. So, these are the characteristics of a population. Now, having noted this now, we'll go into the third level of a population, the third level of ecology. Remember, we are studying levels of organization in ecology. We have talked about the individual species level. We just finished talking about the population. So let's talk about the third one, which is community. And community is very simple to define. When we talk about community, we're talking about the collection of individuals of the same species interacting together within a given area. So you can see that I mentioned in population that these individuals are of the same species. Sorry. These individuals are of the same species. But in the case of community, it's a different ball game altogether. The individuals are not of the same species. They are of different species. You can even study community in the laboratory. If you have a tube that you have different species of organism, probably you have a bacteria, and you have a spirogyra as a different organism, and probably any other microorganism interacting together in that tube, that forms a community. So in the case of community, it involves individuals of different species interacting together in a given area. Okay, so that is it about the levels of organization in a population. So the next thing we want to talk about is okay, all right. So I will lose that when we get to ecological niche. I wanted to talk about different categorization of individuals in a community as producers, consumers, and the decomposers. We'll talk about that later. Let's look at the basic ecological concept. The basic ecological concept. One of the basic ecological concepts is the concept of ecosystem. Just a minute. Okay. So one of the basic ecological concepts is the concept of community. Community. Basic ecological concept is a concept of what? Sorry, is a concept of ecosystem. Hmm? One of the basic ecological concepts is the concept of ecosystem. When we talk about ecosystem, we're talking about a self-sustaining unit that is made up of biotic and abiotic factors. So in a typical ecosystem, that ecosystem should be self-sustaining. That means that everything that everything that is required, sorry, to perpetuate life should be found within the community. The community should not require it from another. The ecosystem should not require it from another ecosystem. So that is why that concept, sorry, that term self-sustaining is used for ecosystem. So a typical ecosystem must be self-sustaining, and again, it must also be made up of the biotic and the abiotic factors. We have so many abiotic factors in the community, like temperature, like humidity, wind, and so on and so forth. These are abiotic factors. Then the living organisms within this ecosystem, like man, like microorganisms, like other animals, like plants, they form the biotic aspect of an ecosystem. And let's take, for instance, a typical pond can be referred to an ecosystem. The ecosystem, of course, should also have the source of energy that comes from the sun, the radiant energy that comes from the sun. And that radiant energy powers all the activities within the ecosystem, in the sense that producers get or harness this energy from the sun, and of course use it to produce food for other organisms at the higher trophic levels. So that is what we're saying, or that's what we mean by ecosystem. And of course, when we talk about ecosystem, we have different types of ecosystem. We have the aquatic ecosystem. Don't forget I said a pond can be referred to an ecosystem. A pond is okay. It will be part of what I'll be saying now. We have aquatic ecosystem and we have terrestrial ecosystem. So the aquatic ecosystem, of course, has to deal with ecosystem that has water in it, and we have organisms that live within that environment. So in the case of aquatic ecosystem now, we have two main types of ecosystem: the freshwater ecosystem and the saltwater ecosystem. The freshwater has uh, little or no salt in them, whereas the salt water, like the sea and the ocean, has salt content in them. So we have the marine ecosystem and the freshwater ecosystem. The freshwater ecosystem, the marine ecosystem is also called the saltwater. Then we have the freshwater. Under freshwater, that is where you see the river, the lakes, and the rest of them. You can even include pond under freshwater. Then, of course, under the marine, you see the ocean and the sea. Then we also have terrestrial ecosystem. So this one talks about the ecosystem on the land, the land ecosystem. So if it's not aquatic, of course, it's land. Then you talk about the different types of a terrestrial ecosystem such as the forest, the desert, the savanna, tropical rainforest, and so on and so forth. So that is what ecosystem is all about. Remember, I said you should be self-sustaining. Eh? You should be self-sustaining, and it should also be made up of biotic and abiotic factors. All right. So having discussed it now, let's talk about the individuals within the ecosystem. The individuals within the ecosystem. Of course, in a typical ecosystem, this is also studied under ecological niche. You see three different kinds of individuals within the ecosystem. The, the first group of organisms is the one we call the producers. The producers. And these ones are the ones saddled with the responsibility to harness the sun's energy and, of course, use it to produce food for other organisms at higher trophic levels. Then, apart from the producers, we have the consumers. These ones are directly dependent on the producers. As a matter of fact, if there is no radiant energy or sun's energy and there is no plants, then of course life on Earth would cease because life on Earth is dependent on this interaction that is this between producers and the radiant energy. So all consumers are directly dependent on plants, autotrophs. Without autotrophs, life on Earth will cease. So if plants, I used to tell my students or teach that if all the plants in the world should have meeting now and say that they are no longer interested in producing food, then of course life will automatically cease on Earth. And some scientists have postulated that life will cease on Earth in the next 1 billion year. Photosynthesis will cease and plants will stop producing food. That is where photosynthesis ceasing, and life will then stop. This is a postulation by some scientists. Nobody actually knows. Nobody actually knows when life will end completely on Earth. But I'm saying that if for any reason photosynthesis stops, that means that life itself will cease. Oh, okay. So that is about consumers. Of course, we'll have different levels of consumers. We'll have the primary consumers, we'll have the secondary consumers, So let's use the food chain. Okay, we are still going to talk about the food chain, but then, so we can also use the food chain to talk about these different types of consumers. So when we get to food chain, we'll look at it. So I have types of consumer. Then the last group is now the decomposers. These are the three main groups you see in a typical ecosystem, the decomposers. These ones recycle nutrients. And of course, these recycled nutrients are used by the producers to produce their own food. We have bacteria and fungi as the major organisms that belong to this group of decomposers. They are still important. As a matter of fact, without them, it will be difficult for producers to produce their food. So, so all the three different categories of organisms have the role they play in sustaining the ecosystem. So all of them are equally important. Then I talked about the non-living part of the ecosystem. Okay. So now it's time to talk about the food chain. Now it's time to talk about the food chain. I hope this can be seen. Now it's time to talk about the food chain. The food chain. Food chain. This is another basic ecological concept. Remember, we're talking about basic ecological concept. We're talking about the ecosystem. Now it's time to talk about the food chain. The food chain. When I was talking about aquatic environment, aquatic ecosystem, now I said we have two: the freshwater and the marine, the salt water. Of course, we have the estuarine, estuarine, where fresh water mixes with the the salt water, but it's not as popular as the marine and the freshwater. So when we talk about the food chain, when we talk about the food chain, we're talking about the feeding relationship. As organisms are found within this ecosystem, these organisms actually interact, like I've said before now, and this interaction could be through the the food they eat, or the things they feed on. So there is a transfer of energy through this food from one trophic level to another trophic level. So one can now comfortably say that the linear food relationship that exists between organisms is referred to as a food chain. Or somebody can also say the transfer of food from one trophic level to another trophic level in a linear pattern. That word linear has to be there for it to be called a food chain. Since we have another type that forms a network, which is now called the food web, the interconnected food chain is now what they call a food web. So in the case of food chain, we'll have the producer, this is the grass, the producer, they'll have the grasshopper, we'll have the grasshopper, then we'll have the lizard, for instance, they will have snake, they will have hawk. So in this case now, you see that grass is known as the producer or the autotroph in this case. So the grass is the autotroph or producer. Then in the case of grasshopper, grasshopper is a consumer. And what kind of consumer? This one, primary consumer. Primary consumer. So grasshopper is a primary consumer. Then we have another one that is called the lizard. This lizard is feeding on grasshopper. While writing this, uh, while writing this food chain, it's important you know how best to position the arrow. If this arrow is positioned this way, it means that the grass is feeding on grasshopper, and that will be wrong. So where the arrow is pointing to shows the organism that is feeding from the other organism where the arrow is coming from. So in this case now, the arrow is pointing towards grasshopper. It means that grasshopper is feeding on grass. Then the lizard is now referred to as the secondary consumer. Then the snake, of course, is referred to as the tertiary consumer. Then is now hawk hawk in this case, most people are familiar with primary, secondary, and tertiary, and that's correct. But we still have the one they call the quaternary consumers. So in this food chain that we have drawn, hawk can now be referred to as the quaternary consumer. But then the food chain is not complete. And why is it not complete? It's not complete because we did not add the consumer, the decomposer, sorry. We did not add the decomposer. So this has made the food chain to be complete because we have now added the decomposer. So you can see how this food chain is transferred. Sorry, how food this yes, how this food chain is arranged linearly, in the linear form. That makes it food chain. Food chain. Then the next one is what we call the next one is what the one we call the food web. The food web. The food web. Just a minute. So the food chain can form a network of other food chains, can form a network of other food chains. And this network of other food chains is what we call food web. For instance, one, two, three can form a food chain on its own because this is a green plant on the grass. The field mice is feeding on grass. The hawk is feeding on field mice. It's a food chain. Hmm? Then we have green plants, insect, lizard, hawk. One, two, three, four is another food chain. Then green plants, insect, hawk is another food chain. Then green plant, worm, toad, and even snake is another food chain. So you can bring out so many food chains that are interconnected, hmm, interconnected, that forms a network. And this interconnection of food chains forming a network is what we call the food web. That's what they call the food web. So in this case now, you can see the green plant, which is the producer. Worm feeds on green plant. Then field mice also feed on green plant. Then coming up to this level, the primary producer, primary consumer, will have that the insect is being fed by toad. Then toad also feeds on worm. Hawk can directly feed on insects, whereas lizard can feed on insects. Then this snake feeds on toad, but snake can also feed on lizard, and hawk can feed on snake, and hawk can feed on lizard too, and hawk can also directly feed on insects. So this is what we refer to as the food chain, the interconnection of other food. Sorry, this is what we refer to as the food web, the interconnection of other food chain. All right. But then you have to understand that this kind of food chain is a terrestrial food chain. Hmm? Of course, there is no aquatic organism here. All these things occurs on land. So this is an example of terrestrial food chain. We still have aquatic food chain. So let me see if I can use. Let me draw this to to explain the aquatic food chain. But then it's basically the same thing. The only difference is that aquatic food web aquatic food web occurs in water. Hmm? So how this has green algae, or have crustacean, then we have small fish feeding on the green algae. They will have the dragonfly nymph feeding on the small fish. They'll have the large fish. Then of course we'll have the crocodile. The crocodile too is feeding on the dragonfly nymph. Then we'll have this. So this is another food web. You can also see the producer, which is the green algae. Small fish feeds on this green algae. Then the crustaceans too feeds on the green algae. Large fish sometimes also feed on green algae. Then crocodile feeds on the large fish or the big fish. Then the dragonfly nymph feeds on the small fish. Whereas the crocodile also feeds on the dragonfly nymph, and the dragonfly nymph also feeds on the crustacean. So one, two, three can be a food chain. One, two, three is another food chain. In fact, one, two, three, four is another food chain. Then one, two, three is another food chain. So you can see how many food chains come together to form a food web. So that's the concept of food chain and food web. So the next one we're going to talk about is ecological pyramid. So when we talk about ecological pyramids, we are looking at the graphical representation of the relationship that exists between different organisms in an ecosystem. When you now begin to look at these different organisms that interact together and their relationship, and you want to now represent it graphically, that, that is what is called ecological pyramids. We have different types of ecological pyramids. We have the pyramid of energy, we have the pyramid of number, we also have the pyramid of biomass or weight. All these things are studied within the ecological pyramid. So we are going to be looking at them one after the other. Let's look at the pyramid of energy. The pyramid of energy. So this pyramid of energy, I said we have three different types of ecological pyramids: pyramid of energy, pyramid of number, and pyramid of biomass. Biomass talks about the weight of an organism. The weight of an organism. That's what we call the biomass. So, in the case of pyramid of energy, we are talking about the rate at which energy is transferred from one trophic level to another trophic level. Hmm? So, when you now represent it graphically, the rate of transfer of energy from one trophic level to another, that is what you are doing when you're talking about, or that is what pyramid of energy is, or is all about. When you talk about the rate at which energy is transferred from one trophic level to another trophic level. And I think by the time we get to thermodynamics, I will say much. I will say more about this transfer of energy from one trophic level to another trophic level. So for now, let's just please let's just concentrate on let's just concentrate on this definition. So if I have a structure like this, if I have a structure like this, I have this 2, 3, 4, 5. So in this case now, So let's assume that we have this, we have this. So of course you know that energy is measured in kilojoule. You know that energy is measured in kilojoule. So this explains the pyramid of energy. This is a green plant, and the green plant has the highest number of energy, which of course it's harnessed from the sun. And as we went to the next one, which is the grasshopper, then you discover that the energy further reduced at the third trophic level. This is the first, second, third, fourth, fifth. So at this trophic level, you discover that the energy further reduced to about 50 times 10 raised to the power 4. Then at this other level again, the energy also reduced. Then it became the least. So top predators, or individuals at the highest level of this pyramid have little amount of energy left. So by the time we get to the law of thermodynamics, we'll explain further how uh, this energy goes, or when we get to productivity, or is also what is studied in productivity. We will also look at how this energy is transferred and the quantity of energy that is transferred from one trophic level to another trophic level. So this explains the this explains this explains like I said, this is trophic level 5, this is 4, this is 3, this is 2, this is 1. So let's now look at the second one, which is pyramid of biomass. Pyramid of biomass. So pyramid of biomass refers to the total dry weight of an organism. The total dry weight of an organism explains the pyramid of biomass. Pyramid of biomass. So the same green plants. I want to clean this. They have grasshopper, we have lizard, we have snake, we have hawk. So if you so we can have this as 5,000 tons, then 900 tons, 100 tons, then maybe 5 tons, and 1 ton. So this refers to the total dry weight of organisms within this within this uh, within the ecosystem. So you can see that green plants have the highest weight. Green plants have the highest weight. They have about 5,000 tons, and that is also show that there are many. Okay, the fact that there are many will be studied under pyramid of number. So let me be specific so that you don't misunderstand what I'm saying. But I actually uh, uh, had a reason why I mentioned that. But so that I don't confuse you, let me maintain what we are talking about under pyramid of biomass. So in terms of weight, green plants have the highest number of weight, followed by the grasshopper, that is individuals at the second trophic level. And you discover that at the fifth trophic level, which is the last one, the energy dropped from 5,000 to 1 ton. That is to also show or to also indicate that as individuals, as we get to other trophic level, the number of energy reduces drastically. Then of course, the last one is the last one is the pyramid of number. The pyramid of number, which is a graphical representation of the number of organisms at each trophic level. The graphical representation of the number of organisms at each trophic level. That is what we call the pyramid of number. So here we still have green plants. We still have green plants. Then we have the grasshopper, the grasshopper. Then here we have the lizard first. Then we have snake. Then we have hawk. So let's assume we have 500 green plants. Or let's just say 5,000 green plants. When they get here, you may have like, let's say, uh, 1,000. 1,000. Remember, this is an estimate. We're just using this to explain something. This is an estimate. Then, when you get to this third trophic level, this is third, this is second, this is one, this is fourth, this is fifth. Then you can have like maybe let me say, 300, then maybe 70, and maybe 5. So if you use what you have in your textbook, in the textbook, you can now say very many, very many. Then here we can use many. Then here we can use 80 to 120. Here we can use 15 to 30. Here we can use 30 to 4. So this thing and this thing, they're still explaining the same thing. This very many shows that 5,000 also shows that it's very many. So the organisms at the first trophic level are so many. You cannot count the number of plants we have or the number of autotrophs. There are so many. There are so many. And they are of different species. So many. So many. And that is what we are representing here. Remember, this is a pyramid of number. We've talked about pyramid of energy. We've talked about pyramid of biomass. Now is the pyramid of number. Pyramid of number. So the same way energy reduces as you step forward the trophic levels, as you go through the trophic levels. This and also the same way that the biomass, total biomass also reduces. The same thing happens to number. And because the level of the amount of energy that is transferred to individuals at the fifth trophic level or the upper trophic level is reduced, so we don't have so much number of them. Green plants are the ones manufacturing their food. They're the ones cooking the food. So they tend to, have higher number or will have higher number of them because they're the one producing the food for us. As you now climb the trophic level, you discover that this number begins to dwindle, begins to reduce. A minute. So that is it. I don't want this video to be too long. Once it's 1 hour, we shut down and continue in part 2. So let's now talk about energy flow in the ecosystem. Energy flow So, under this energy flow in the ecosystem, we will also be talking about the two laws of thermodynamics. Of course, you know that the energy that is used within the ecosystem comes from the sun, and that is called the radiant energy. And like I've explained, this radiant energy is harnessed by the green plants, sorry, by the autotrophs, and of course, transfer the same energy to the heterotrophs or the consumers as you move along the trophic levels. So the way this energy flows, there's a man they call Raymond Linderman. Raymond. Raymond. So this man was the one who coined what is called the 10% energy rule. The 10%, the 10%, the 10% energy energy rule. And based on what he said that it is only 10% of the energy that is transferred from one trophic level to another trophic level. So at the end, he discovered that individuals at the highest trophic level, or let me say the fifth trophic level, may have maybe zero point 0.1 of the entire unit of energy. So let's take for instance, that 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 let's take for instance that we have 100,000 of radiant energy, 100,000 of radiant energy. Now, out of this 100,000 of radiant energy, the plant, of course, you know that the plant cannot absorb all the radiant energy. It's not possible. Hmm? Not possible. So some are even reflected back to the atmosphere. So let's assume that it is about because usually 1%. Usually 1%. Usually 1%. Let me assume that the sum that the green plant absorbed 1% of this radiant energy. So 1% of 1,000 will give you, is it not 1,000 units? 1,000 times, is it 1,000 or 10,000? That should be 10,000 now. That should be 10,000 units. 10,000 units of energy. Then, okay, so if we have 10,000 units of energy absorbed by the plant, then 10% of this 10,000, 10% of this 10,000 will of course give you 1,000. So it means that the plant absorbs only 1,000, only 10,000, only 10,000. I'm putting less money too much. Then that means that the plant absorbs only 10,000 units of this energy. And if the plant, which is the organism at the first trophic level, absorbs 10,000 units of the energy, 10,000 units of the energy, then of course the individuals at trophic level 2 will absorb 10% of this 10,000. 10% of this 10,000. Why is it just 10% that the is being transferred? So what happens to other energy, other 90% of the units of energy? Some of them are lost as heat, and some of them are utilized by the organism for their own metabolism. Hmm? Because they also require it. Even consumers, the consumers in traffic level 2 cannot even transfer everything. It's still the 10%. That is what Raymond studied. So it is 10% that is transferred from one traffic level to another traffic level. So if we have this That means that these people now got 1,000 units. That means the traffic level 2 was happening to my marker. Just a minute, let me get another marker. So that means that individuals, that means that these people got yeah, that's correct now. That's 10,000. I was trying to see if 10% of okay, yes, 1%. I mentioned I mentioned 1%. So I mentioned 1%. 1% of 10,000 is not 1,000. Yes, she 1,000. So let me repeat what I said. Mm. So what I was saying is that the green plants, if you have if you have if you have 10,000 units of energy, of energy, then of course the green plants will absorb maybe 1%. 1%. 1% of 10,000 of 100,000 will give you about 1,000 units of energy. 1%, that is 1 over 100 times by 100,000 over 1, this. So it gives us 1,000. Gives us 1,000. So we have that the green plant, which is at trophic level 1, will have 1,000 units. 1,000 units of energy. Then individuals at trophic level 2 will have 10% of 1,000. And 10% of 1,000 will give you 100 units of energy. Then individual at trophic level 3 will have 10% of 100. And 10% of 100 will give you how many? Will give you 10. Then of course, the last group, or the individual at trophic level 2, will now have 10% of 100, sorry, 10% of 10, which is 1 unit of energy. 1 unit of energy. So this one unit divided by the initial unit, wow, that is 100,000, give you about what will it give us? 0.0001, 0.001, 0.001. Is that correct? Have this 1, 2, 3, 1, 2, 3, 4. Okay, let me not confuse you anymore. So let me leave that part. So what we're trying to say is that if you have 100,000 units of energy, I mean radiant energy, out of this 100,000 units of energy, plants usually absorb like 1%. Plants usually absorb like 1%. At the end of the day, once they absorb that 1%, that means that they absorbed like 1,000 units of energy. 10% of that unit is transferred to individuals at the next trophic level. So individuals at the next trophic level continue to get 1%, 1%, 1%, 1%. So, sorry, 10%, not 1%. Individuals at the next trophic level. So, if these people if plants absorb 1,000 units of energy, 10% of this 1,000 is 100. That means that it is 100 units of energy that they have transferred to the primary consumer. And of course, the primary consumer that absorbed this 100 will now transfer only 10% of 100, and 10% of 100 is 10 units. Then this secondary consumer that absorb 10 units can only transfer 10% of his 10 units, and 10% of 10 units will give you 1 unit. Hmm? To give you 1 unit. So 1 unit is the level of oxygen, sorry, the energy that is being gotten by the individuals at the fourth trophic level. So this is how the Raymond Linderman's 10th rule, 10% energy rule works. 10% energy rule. Just a minute. So let me conclude so that in our next class we'll talk about the second part of ecology. Like I said, this topic is so vast. It's not something that we can conclude in a day. It's so vast, so vast. All right. So let's look at what's the time? This is already 1 hour. So I think we're gonna stop here. Hmm? We're gonna stop here. But then, have I thought about the laws of thermodynamics? Okay, let me quickly say it before we go. The laws of thermodynamics, we have two. The first one says that energy cannot be destroyed or created, but can be transformed from one form to another. Then, uh, what is just trying to say that you this energy that you is being gotten from the sun can only be changed from one form to another, but cannot be destroyed. Like we said that some of them are lost as heat. So the remaining percentage of the energy that uh, uh, were not captured in all this calculation, you cannot say that they have been destroyed. They were not destroyed actually. Some of them were lost as heat. So energy cannot be destroyed, hmm, but or created, but can be transformed from one form to the another, to the other. And the second law now says that the energy transformation in an ecosystem is not entirely efficient, is not completely efficient. And it means this now I just said now, energy transformation in an ecosystem is not entirely efficient. That means that there is no individual in a trophic level that absorbs energy and transfers the same amount of energy to the other individuals at the next trophic level. It is only 10% that is transferred to individuals at the next trophic level. So this explains the second law of thermodynamics, which says that energy transformation in an ecosystem is not entirely efficient. So in our next class, there are other aspects of this ecology that we're going to talk about. So see you in my next class.